All right, Master Science students, let's look at now the final part of this this section on the mechanisms, and in this time we're going to be looking at this effect called the kinetic isotope effect. Uh, this comes from the observation that uh, the breakage of carbon hydrogen bond. You're talking about, okay, let me say, the rate at which the carbon hydrogen bond breaks and the rate at which, if you've replaced it with the one with its isotope, which has got an extra, which has got a neutron, like in this case it's deuterium, uh, the rate of the breaking of the carbon hydrogen bond, and if you're going to measure the rate in which, for example, if you've got a way in which you are forming an enol, so that in this case you've got something like an acetone, and then you're putting it in sodium hydroxide, and then you're seeing at what rate does all the hydrogens, does the alpha hydrogen next to the carbonyl group gets deprotonated by the hydroxide. Maybe it can be something like maybe 30 seconds, yeah? And then you do the same reaction, but in this case you've replaced the carbon next to the carbonyl group with the deuterium atoms. So probably in this case, rather than maybe 30 seconds, it may be something like maybe 2 or 3 minutes, yeah? So in this case, what you're saying is that the rate at which uh, the ratio of the rate uh, in which the hydrogen to the deuterium, uh, that ratio is called that ratio becomes significant if the if the if the bond which is breaking is the rate determining step. If the carbon hydrogen bond is the rate determining step. Yeah, so that in this case, so the ratio can range from 1.0 if there is no carbon hydrogen bond breaking in the rate determining step. But if it is breaking in the carbon hydrogen in the rate determining step, then the rate can change to about 6.0 to about 7.0. Yeah. Yeah. So in this case, the rate in which the carbon hydrogen bond is much greater than the rate at which you've got deuterium. So the value is always it will be positive. So in this case, you're mentioning that the rate in which the hydrogens are replaced with deuterium. In this case, the rate in which the hydrogens are unchanged. So in this case, there are two types of kinetic isotope effect, and I'm going to illustrate here. So there is the primary kinetic isotope effect, and then there is the secondary kinetic isotope effect, in which there is a rate determining step, but the carbon hydrogen bond breakage is not in the rate determining step. That's called the secondary kinetic isotope effect. And in that case, the value of between hydrogen and deuterium will be close to 1. Yeah. So in this case, let's look at this reaction here. A typical type of reaction in which there is the benzene group, and then there are two hydrogens, there's a CH2, and then there's an alkyl group, and then you've got an ethoxide. So the ethoxide group is doing, I think you now know the mechanism. The ethoxide is going to abstract a proton. This thing is coming here, and then the bromide is leaving. Can you see that? It's attacking the hydrogen, so you're forming a double bond. Yeah. So if that one is the rate determining step, then there will be a significant difference between the rate where you've got the hydrogen and deuterium. So in the second case, the hydrogens next to the benzene ring were replaced with deuterium. And then the same reaction was done. So the ratio of the rate between the two was 7.1. So that tells you that there is carbon hydrogen bond breakage in the rate determining step. So in this case, this just saying in one case, like in this case, I'm having a hydrogen here, and in this other case, because deuterium is being removed, then the atom here will be deuterium. So when you see H in bracket D, it means that in one case you're having deuterium, in the other case you've got hydrogen, yeah? Okay. So in this case, you've got the famous reaction that you know, the nitration of benzene. So you've got the benzene attacking the nitro group, which is formed by the reaction between the sulfuric acid and the nitric acid. So they are the ones who generate the nitro group, and then the nitro group attacks the benzene group attacks the nitro group. So in this case, this is the rate determining step there, the attack of the benzene, the aromatic ring with the nitro group. And then once you've protonated the benzene ring, then the proton falling off to restore aromaticity is normally a fast reaction. So in this case, the rate determining step is not the breakage of the carbon hydrogen bond. So there is please note this, there is a breakage of the carbon hydrogen bond, but in this case, that one is not the rate determining step. So in this case, the ratio of the rate between the hydrogen and the deuterium is 1.0. So it's telling you that there is no breakage of the carbon hydrogen bond in the rate determining step. That tells you to be able to get your mechanism correctly. If you're just given those figures, like in this case, you can be given KH to KD to be 7.1. In this other case, you are given 1.0. So you can be able to come up with the proper mechanism and just say, hey, this is the rate determining step. The rate determining step in this case does not involve the carbon hydrogen bond breakage. Are you clear on that? Now, what scientists have found out, and I think this is the last thing I will be mentioning, is that you're going to get a lot of information if you're going to combine the Hammett plot. In this case, it is the raw values with the kinetic isotope effect. Like in this case, you've got a phenolic ion. It's attacking this complex in which there's a benzene group, there's another benzene group, and then there's a sulfonate group. What scientists have done is to map out the raw values for each of the ring. In this case, for the phenolate here, in this case, you've got your X coming from the methyl, methoxy, what hydrogen, chloride, what cyanide, and then the nitro group. So in this case, you're going to get a what? If you're going to be plotting the curve for just this one only, you can see for it to be reacting, the phenoxide group is going to be leading to, is going to be having what? A decrease in the electron charge. It's going to be moving from a negative charge. If it's going to be attaching a proton, it will be ending up as a phenol. Phenol does not have a negative charge. So in this case, the raw value will be negative. In this case, it is negative. So it's a bit large because the negative charge is attached next to the benzene ring. Can you see that? So the raw value will be negative 4.0. So they also plotted the raw value for when you've got this other aromatic ring. And what has been seen is that if you are going to be plotting for this one, because the electrons are going to be towards the ring, if you're going to be forming a double bond, electrons are coming towards the reaction center. So the rho is going to be what? It's also going to be positive. In this case, it will be positive 2.6. And if you are going to be plotting the one in which there is this sulfonate group here, because the electrons will also be going towards the ring here, towards this reaction center which is next to the ring, but because it's a bit far, 1, 2, 3 atoms away from the ring, then the rho value is going to be positive because the electrons will be going towards and it will be 1.0. Can you see that? So what they observed was that the ratio between uh, the kinetic isotope effect, where you had hydrogen first and then you had the deuterium, was 7.1. So that tells you that there is the breakage, that the breakage of the carbon hydrogen bond is the rate determining step. So in this case, these are the products that you are forming. From this one where you had the X, you are forming a phenol. This one here, you are forming where there is the double bond because this bond is breaking here. And then the electrons are ending up on the oxygen here, so you are forming this sulfonate group. Can you see that? So you're having 3 products, yeah? So can you see, in this case, you have a lot of mechanistic data if you're going to be combining what? The Hammett plots with the kinetic isotope effect data. Yeah. So they are used together to be able to give you mechanistic, information. All right. So I think later I think we may see more examples, but this gives you a very good example in which you can combine the KIE with the Hermetic question. Okay. So I hope you really learned something about the understanding of mechanism based on the Hermetic question and the kinetic isotope effect. Yeah. All right. So I think the next thing which we'll be talking about will be going to the last topic, which is the pericyclic reaction. But we'll begin to talk about basics. Before talking about pericyclic reaction, we'll be giving an overview of the molecular orbital theory. Yeah? Just a little bit, not much mathematics. Yeah, but we'll be focusing on those orbitals, the s orbital and the p orbital. Yeah, that's what we're going to be using. Okay. So I hope you've really enjoyed what you've talked of so far. Okay. So.